All right, the last set of right. Okay, so in our notes last week, we did some stuff with inverse functions, and normally we would have been doing that inverse functions when talking about exponential functions. We talk about inverses, which gets us to logarithms. So we did some quick review of logarithm stuff that we learned first semester. And now we're going to do just a very little bit of what we normally do with logarithms. We usually do a whole lot more, but we want to at least get you guys to see the basics because you will come back to logarithms when you get to pre-calculus your next year or your senior year, one of the two. So these three properties are the properties of logarithms that we focus on a whole lot, and they will kind of look familiar. So the first one here, we've got log base b of something, or mn, like m times n. We can change that and separate the m and the n to be log base b of m plus log base b of n. This should look familiar to a rule where we have, if you've got something raised to an exponent and then times something raised to another exponent, as long as they have the same base, we can multiply, or I'm sorry, add those exponents, right? M plus n. Remember that rule with exponents? That's where the same rule comes from with logs. The same kind of thing, because remember, logs and exponential are inverses of each other, inverse functions of each other. So that's where that rule comes from. The next one, we've then got division of logarithms turns into subtraction, and we can separate it. And again, if you guys remember, if you've got a to the m over a to the n, that's the same as a to the m minus n, right? And finally, our last one, we've got if you've got something to a power, that power can come out in front of something, right? So that one's a little bit different, but again, comparable to the rule where if I've got a power raised to a power, then that becomes a to the m times n. And over here, if I've got something raised to the power comes out in front to be multiplied by the log. Okay, so kind of helps to remember your exponential rules to kind of see how these new logarithm properties work, but they're kind of following those same basic rules. Okay, so let's see how these work on a couple problems. So, and we'll go both directions here. So sometimes we'll start on the left side and move to the right. Sometimes we'll start on the right side, move to the left. But these properties can go both directions, from left to right or right to left. Okay, so when we go from left to right, that is called expanding a logarithmic expression. So that's when we start with something like log base 3 of 12x, and we're going to expand it into more than one logarithm. Okay, so it's log base 3, so we're always going to keep that base the same. That's not going to change. And then I'm going to look at what operation is happening here with what I'm taking the log of, right? So this is log base 3 of 12 times x. There's multiplication happening between those two things. So I can separate that multiplication into two separate logs. So I'm going to rewrite this as log, if I can spell log right, log base 3, that base stays the same, of 12, and then my multiplication, if I'm multiplying, that can separate into addition. So that I'm going to add log base 3 of x, right? So I took the 12 times x and separated it into two logarithms. So I get log base 3 of 12 plus log base 3 of x. Okay, so you can expand a logarithm. All right, let's look at a couple more here. So the next one, log base 2 of a divided by 7. Again, that's what I'm taking the logarithm of. My base is going to stay the same, but I'm going to separate that division into two separate logarithms. So that's like our property number 2 up on the top, right? We're doing division, so we're going to turn this into subtraction of logarithms. So this one would become log base 2 of a is on the top, right? And remember, division, the order matters. So like on our multiplication one over here, I could have had 12 first and then x, or x and then 12. It doesn't matter because 12 times x is the same as x times 12. But on the division and the subtraction, the order does matter. So whatever is on the top is what I want to go first in my subtraction. And then I'm going to do minus log base 2 of 7, right? So the numerator of the division goes first, denominator of the division goes second, but we made that division into subtraction. Okay, and then finally our last one here, I'm seeing how the exponent rule or the power rule works. So again, keep your base the same. So I'm going to keep my log base 6. And then basically the easiest way to remember this one is anytime you have an exponent where that is something that you're taking the log of, that exponent can come out in front. So I'm going to do 10 times log base 6 of z. Okay, and we'll kind of see what this helps us do here in the next couple sections. Okay, so that's one rule at a time. Now let's look at a couple where we kind of put these rules together and have to do more than one thing, right? Okay, so this first one, we've got log base 2 of 7x cubed over y, right? So I've got a 7 times x. That x has an exponent on it, and then I also have division by y. So we've got several different steps here, right? Okay, so we could first separate and do the division, or we could do the multiplication on the top. It's not a huge deal here what order you need to do it in. As you get practice, you'll get a little better at it. So I'm going to start with that division step. So I'm going to change this into log base 2 of 7x cubed is what's on the top, right? Minus log base 2 of y. So the first thing I did there was I took away the division and separated that into two subtraction logs, right? Okay, then I've got the 7x cubed. So this is 7 times x cubed. So I can separate those two with addition because I'm multiplying those two numbers. So this would become log base 2 of 7 plus log base 2 of x cubed. And then we still have minus log base 2 of y. Okay, so multiplication of the first two and then subtraction. If it helps, if you want to, you can put this in parentheses. But in that case, the parentheses, you don't have to have them there, but if it kind of helps you see how it works, you can do that. Okay, but you don't have to have them there. Okay, and then lastly, I've got an x cubed, so that exponent can go out in the front. So I'm going to make this log base 2 of 7 plus, I'm going to take that x cubed and I'm going to put the 3 out in front, 3 times log base 2 of x minus log base 2 of y. Okay, that's as much expanding as we can do. And basically the way you know is once you've got it expanded is the thing you're taking the logarithm of is just one single term. So just a 7, just the x, and just the y, right? So there's our completely expanded expression. All right, let's try one more over here. And again, this time we've got a square root of x, and then we've also got some division, right? So that's log base 10, so that base is going to stay the same. So I'm going to do the division first. We've got log base 10, and we'll separate the radical x. And then because it's division, I'm going to make it minus log base 10 of 5, right? We're separating that division and making it into two logs with subtraction. Okay, then I've got this square root of x thing that we've got to deal with. So remember, radical x, I can also write that as a rational exponent. So I can also write that as x to the 1/2 power, right? So I'm going to rewrite my radical x as x to the 1/2 power. And then once I've got it as an exponent, now I can take that exponent and put it in front of my logarithm. That would be 1/2 times log base 10 of x minus log base 10 of 5. And that's as much expanding as we can do on that expression. Okay, These can get a little bit tricky, so just kind of try them. Try it first, look at the answer. If you get it wrong, try it again, like erase it and try it again. Or if you still get stuck and can't figure out how you got the answer, how I got the answer, please send me a question, okay? I'll help you out. Okay, so that's expanding an expression, right? Starting with one logarithm, expanding it into multiple logarithms. Now we're going to do it the opposite way. So now we're going to condense a logarithmic expression. So now I've got multiple logarithms and I want to condense it down to just one logarithm per problem. Okay. And again, this is the same three properties up here, except now we're starting with an expression like on the right side and moving to something on the left. We're going the opposite direction. Okay. So on this one, we'll start here on the first one. So I've got, now the other catch here is, remember your bases have to be the same. If that was a base 5 and a base 7, then I couldn't do anything with this at all. The only way these properties work are as if I have the same base. Just like with your exponent rules, you can only do those properties of exponents if you have the same base with your exponential equation. The same thing here, bases and the logarithms have to be the same. Okay, so I've got subtraction, correct? So if I'm subtracting the logarithms, I can condense that into the logarithm of those things being divided, right? So I'm going to write my same logarithm with the same base, so log base 5. And then instead of the subtraction, I'm going to condense it and I turn it into division. So it would be 28 over 7, right? And I can actually do 28 divided by 7. So I would write this as log base 5 of 4. And there is our condensed logarithmic expression. So see, sometimes when I condense them, it actually makes it a little bit simpler. Okay, the next one. Now this time we've got addition. This time we have 3 logarithms, and then again, notice they're all the same base. That's what we want to happen, right? Okay, so if it's addition, we can condense them down into multiplication. And you can do them 2 at a time, or you can do them all at once. That's up to you. But this would become log base 3. And then I'm going to multiply all 3 of those things because it's all addition, right? So I could do x times 3 times 4. And then we can simplify that expression, x times 3 times 4. That would become log base 3 of 12x. Right, there's our condensed expression there. Okay, and then our third rule here, if you've got a number out in front of the logarithm, to condense that, we're going to make that an exponent, right? The opposite of what we did before. When we saw an exponent, we put it out in front. Or if you see a number out in front, you can make it an exponent. So this one will become log base 9 of y to the 6th power. Okay. All right, so there's kind of our 3 rules one at a time. Now let's again do a couple where we combine the rules together. Addition and subtraction. Now, when you've got addition and subtraction, you got to pay attention a little bit to parentheses. We'll see that on the next one, but I tend to find either do what's in the parentheses first, or I like to do the multiplication first. It will make it easier, okay? So I see an addition, which means these 2 things I'm going to multiply, and then I see some subtraction, which means I'm going to end up dividing by this one, right? Okay, so, but before I do that, I'm actually going to look for any numbers out in front, because it's also easier to get those done first. So first I see the 2 out in front, so that's going to become my exponent, right? So I'll get log base 4 of 6 plus, instead of 2 log 4(2), I'm going to get log base 4 of 2 squared minus log base 4 of 3, right? So first thing was our exponent. Okay, now I can look at these 2 are going to be multiplied together, right? So we'll get log base 4 of 6 times 2 squared, and then we've got minus log base 4 of 3. And here's where we might want to kind of simplify that expression a little bit. 2 squared is 4, and then 6 times 4 is 24, right? So I can rewrite that as log base 4 of 24. minus log base 4 of 3. And now that there's subtraction, I'm going to condense that into one logarithm. So it's division. This would be log base 4 of 24 divided by 3. And we can do that division. So that would be log base 4 of 8. Right? Okay. And notice, by the way, on all of these, the base, see how it's a little subscript down by the G? We've talked about that before. Make sure you're writing these correctly so I can tell what number is your base and then what number is the argument. That's what this 8 is called. That's the argument, right? So I should be able to tell the difference between those two numbers. Just erase everything. But if you write it as like log 4, 8, that looks like log of 48, right? Don't make it an exponent up there. That's not what it is. That number should be a base. So it's a subscript. So it should be a little bit smaller and it should be lower than the G. Okay. Okay. Let's try another one where we're kind of combining several rules over here. So this time we see some parentheses, right? So a couple things with that. That means that's the operation we want to do first. But also I have this 1/2 out here, which just like always, I would distribute to both of those logarithms. And distribute means multiply. So I could rewrite this as 1/2 log base 4 of 16 plus 1/2 log base 4 of 4, right? And then we've got minus 3 log base 4 of x. And now again, it's kind of similar to this one over here, right? So I'm going to again do my exponents first. So I've got a 1/2 in front of both of those, right? So this would become log base 4 of 16 to the 1/2 power plus log base 4 of 4 to the 1/2 power. And then I've also got a 3 in front of this one. So it would become log base 4 of x cubed. Okay, so we did all of our exponents. I'm also, though, going to think about that 1/2 power. Remember, anything to the 1/2 power, that's the same as doing the square root. So I could think of this as log base 4, the square root of 16, plus log base 4, square root of 4. And this last guy I'll leave the same. And the reason for doing that again is, well, 16 and 4 are both perfect squares, right? So we could simplify that. Log base 4, the square root of 16 is 4. And then log base 4, the square root of 4 is 2. Okay, all right, then I'm going to go with my addition part first. I'm going to do that multiplication. So these two would become log base 4 of 4 times 2. And we can do the 4 times 2, right? And again, I'm showing every single step here. As you get used to these, if you can skip a step or two, that's totally fine. Just make sure I can follow your work, right? And I can tell that you know what you're doing. So log base 4 of 8. And now we've got subtraction. And remember, subtraction we can condense down to division. So that would become log base 4 of 8 divided by x cubed. And now I've got it down to just one logarithm, so I've condensed as much as I can. Okay. All right, so there's our condensing of logarithms, kind of doing it backwards from expanding. Okay, so now that we've kind of seen how to use those properties, let's see what they're used for. So the first one we'll look at is an application of expanding, right? Like, why do I want to take one logarithm and expand it into more than one? Well, if you've looked at your calculator lately, you might notice that there is a logarithm button on your calculator, right? But on your calculator, the logarithm button is always base 10. So we'll kind of make a little note here. On your calculator, it only does, log base 10. There's one other one that does log base E, which is the natural log, which we would normally talk about, but we're not going to this year. But for now, just know that that log button on your calculator is only base 10. So if I wanted to calculate something like we had up here log base 4, right? I can't just type log base 4 of 8 into my calculator. My calculator only does base 10. So instead, we have a couple of things here, but before we had a couple other things with calculators. There used to be a table in the back of a math book that would have certain common logarithm values. Or if you know certain logarithm values, so this problem gives us that log base 5 of 3 is approximately that, and log base 5 of 7 is approximately that number. So if I have those two values, I can use those two to find the values of things that are using those same numbers. Okay, so notice I've got the base 5 of 3, base 5 of 7, and here I want log base 5 of 3 over 7, right? So if I know 3 and I know 7, it would make sense that I'd be able to find 3/7. And the way we can do that is we can expand this expression so that this expression is in terms of these ones that we know, okay? So if I've got log base 5 of 3/7, that's division, right? This right here is dividing or division. So I can expand that to subtraction. So I'm going to change this to log base 5 of 3 minus log base 5 of 7. And then I know those two values from what's given to me up there, right? It said that log base 5 of 3 is actually 0.683. And log base 5 of 7 is 1.209. So then if we do that math in our calculator, 0.683 minus 1.209, we get an approximate value for log base 5 of 3/7 of negative 0.526. All right. So we can expand and then use values we know to find other values. Okay. Next one, kind of the same idea, except this time I've got log base 5 of 21. Okay, so if it's 21, how in the world would 3 and 7 help me? Well, hopefully when I say that, it's obvious to you. 3 times 7 would make 21, right? So what if I rewrite this logarithm as log base 5 of 3, oops, that's a 7, sorry, of 3 times 7. That still means the same thing, right? 3 times 7 is 21. Well, but if I write it as a multiplication problem, now I can expand that, and multiplication I can change into addition of multiple logs. So I get log base 5 of 3 plus log base 5 of 7. And those are those two logarithms we know, right, from the directions. So again, I can replace with their values. So this would be 0.683 plus 1.209. And if we add those together, 0.683 plus 1.209, we get an approximation for log base 5 of 21 is approximately 1.892. I say approximately because we're rounding here, right? Okay. All right, and then last but not least, log base 5 of 49. So again, I know 3 and 7. Can I use 3s or can I use 7s to make 49? That's always your question here. When you're given some values and you have to come up with a new one, ask yourself, how do I make 49? Well, the 3 is not going to help me much, but I do know that 7 times 7 is 49, or 7 squared, right? So I'm going to rewrite this as log base 5 of 7 squared, because 7 squared is 49. And then I can use my properties to pull that exponent of 2 out in front. So that would become 2 times log base 5 of 7. And then I know what log base 5 of 7 is. That one's given to me in the directions. So I get 2 times 1.209. And if we do that in our calculator, we get an approximate value for log base 5 of 49 to be 2.418. Okay, So that's kind of one thing that we've used expanding logarithms for. You can write out other things to get other values. Okay. All right. Much more commonly used for an application is condensing logarithms. Condensing is used a lot more because we use it to solve equations. Okay. All right, so a couple things here. We've got a logarithmic equation. Notice our bases are all the same, which means we can do some condensing here. If I can condense them, then I might be able to solve this. Okay, so on the left side here, I've got subtraction of two logarithms with the same base. I'm going to condense that down to one base. So that gives us log base 8. And now instead of x and then minus long base 8 of 9, I can make that into division. So that would be x over 9, right? Equals log base 8 of 3. Okay, now how this helps us is now notice you've got log base 8 of something on one side of the equation and then log base 8 of something on the other side of the equation. So remember, we talked about in the last notes that a logarithmic equation or a logarithmic function and an exponential function are inverses of each other. So if I want to get rid of those logarithms, I can use an exponential function. So really what's happening here is I am going to do 8 to that power, like this, equals 8 to this power. Right? And what happens when you do that is that the exponential and the log part cancel each other out. The exponential and the log part cancel each other out. And then all that's left is our x over 9 equals 3. The other way, if you just kind of want to remember a shortcut to get from here to here, all we do is drop the logs. Right? If you have a logarithm, just one logarithm on each side of the equation that has the same base, you can drop the logs and solve what's left over. Because now I just have a linear equation that I can solve, right? If I've got x over 9 equals 3, to solve for x, I'm just going to multiply both sides by 9, and we get x equals 27. Right? Okay, now there is one catch to solving logarithmic equations. We do also have to make sure that, if you remember, this was back notes from last semester, and it was also written in the notes from last week, the argument of a logarithm has to be positive, right? So we'll write that down here. The argument, if I can spell argument right, argument of a logarithm must be positive. So I ended up with a positive 27 here. If I were to put that back in up here for x, that would be a positive argument for that logarithm. So we're okay, it checks out. Okay, so on a logarithmic equation, you do have to kind of check your answer a little bit. You don't have to completely plug it in and solve. You just have to make sure that when you plug it back in for x, you still end up with a positive argument. So whatever you're taking the logarithm of has to be positive. If we had ended up with an answer of negative 12, negative 12 would not work because then I'd have the logarithm of a negative number. So I'd end up with no solution. Okay. So argument of a logarithm has to be positive when you plug it back in. You don't have to end up with a positive answer always, but when you plug it back in, it has to be. Okay. All right, let's try another one of these. So another equation here. Again, all the logarithms are base 7, so that's a good start. But we want to condense these so then we can drop the logarithm on each side, right? So on the left side, I've got a number out in front here, so I can rewrite that as log base 7 of x squared, right? Oops, not 21, just squared. Equals, on this side, no numbers in front, so I don't have to worry about that. But I've got addition, so I can change that to multiplication of my two arguments. So I'm going to do log base 7 of 27 times 3, right? Okay, so that would give us log base 7 of x squared equals log base 7. 27 times 3 is 81. Okay, so there's my log 7 and log 7, one logarithm on each side that both have the same base. I can just drop the logarithms. Right, I'll write it here, drop the logs. And then we end up with x squared equals 81. Right, and I'll say again here, we have the same base. Okay, so then I can solve that pretty easily, right? We can take the square root of each side. So if I've got x squared equals 81, I take the square root of each side. We end up with x equals, gotta be a little bit careful here. You will probably want to say 9, but it's not just 9. It's got to be plus or minus 9, right? Because we're taking the square root to solve something. So we've actually got two answers. We could say x equals 9 and x equals negative 9. But here's where, remember, your argument has to be positive, right? So if I go check these, has to be positive. So if I plug them back in up here for x, here's my only x, right? If I plug in 9, I'm good. The argument's positive. If I plug in negative 9, that does not give me a positive argument. So actually, that answer doesn't work. My only answer here is x equals 9. Okay? It can only be an answer if when you plug it back in, it makes a positive argument. Okay. All right, so there's kind of how to solve logarithmic equations by using condensing. We can condense them down to one logarithm on each side that has the same base. We can then just drop the logs and solve the equation that's left over. So then you just got to make sure your argument's positive. Okay, one last thing here. Let's see how to solve one other type of logarithmic equation. These you'll notice that there's only one logarithm. So we've only got a log on one side, right? Now to solve these, we're just going to basically use our definition of a logarithm and we're going to change it into exponential form. So to do these, we're going to change to exponential form. Okay, because I can't just drop the logarithm. The only way you can drop it is if you have a log on both sides. Since I only have on one side, I'm going to use that kind of rhyme we talked about before. The base becomes the base. The other two switcheroos. We're going to change this to exponential form. So my base is 5. So my exponential base becomes 5. The answer to a logarithm is an exponent. So that becomes my exponent. And then that's going to equal the argument, which is 3x plus 1, right? So then that means I end up with 25 equals 3x plus 1, and we can solve that, right? Subtract 1 on each side, I get 3x equals 24, and then divide by 3, we get x equals 8. If I plug that back in to double check it, right, I would get log, I do a quick check here, log base 5 of 3 times 8 plus 1. And that would be log base 5. This would be 24 plus 1, so of 25, right? We ended up with a positive argument. So that means our answer checks out. So we're good. Okay. All right, let's try one more of these. Again, same thing. We have a logarithm just on one side of the equation. So we're just going to use that rhyme, right? The base becomes the base. So the base is 9. The answer is the exponent. So it'd be 9 to the first power equals my argument. Make an extra mark there. Oh, wait, there we go. Equals x plus 15. And then again, we can solve that, right? 9 to the first is just 9. And then we want to subtract 15 on both sides. So we'd get negative 6 equals x, right? Okay, so then if I quickly check that, notice this time we got a negative answer, right? That doesn't mean it's no solution. You might be allowed to get a negative answer. We have to plug it back in. So that would be log base 9 of negative 6 plus 15 equals 1. So we end up with log base 9 of 9, right? That's still a positive argument. So even though we got a negative answer, when we plug it back in, we still end up with a positive argument. So that's fine. That is an answer, right? The only time it's not okay is if when you plug it back in, you get a negative argument inside that parentheses. So if I had maybe gotten an answer here of like negative 20, right? If I had done like, if you get log base 9 of say negative 20 plus 15 equals 1, right? Then I'd have log base 9 of negative 5. That does not work because that would be a negative argument. So then I would say no solution. Okay. But as long as you end up with a positive argument, your answer is fine. But you always want to kind of quickly check that to make sure. Okay. All right. So there's kind of our very, very basics on logarithms. We talked about expanding the expressions, right? Using the properties to expand. We did condensing, using properties to condense. We can use expanding to approximate values. We can use condensing to solve. If we've got a logarithm of the same base on each side, you drop the log and then solve what's left. And then we can also solve a logarithmic equation if we only have one logarithm by changing it to exponential form. Okay? All right, you've got a short exit ticket today that shouldn't take you much more than maybe 5-10 minutes at the most. Please make sure you're actually trying those problems. Don't just guess. I want you to actually do those 3 problems so that you kind of get a little bit of practice just to kind of cement this material in your head. If you get them wrong, it's totally fine, okay? I want to know if you're getting them wrong because then I know how we're doing on this stuff. If you want to ask about them, please send me a question and I will help you. But if you're just like typing them into PhotoMath and getting the answer, you are doing yourself no favor. I promise, because you're just doing it to get it done. And then when the test comes around next week, you're going to be struggling to know what to do. So please make sure you're actually trying them, okay? We'll have some homework over this on Thursday and then your last test next week. You guys have a good week. I will talk to some of you soon.